Go ahead.
Hello, everyone. I am Leon, a PhD student working in Tufts HCI lab. In this paper, we present a framework to learn brain activity representations from unlabeled NIRS data. This framework quickly adapts a general brain activity encoder to new users and tasks. Thus, it makes the design, development, and the deployment of interactive BCIs more practical. First, I want to introduce NIRS, aka Functional Near-Infrared Spectroscopy. It measures the changes in oxy and deoxyhemoglobin. By monitoring the changes, we can infer users' mental workload dynamically. This technology provides a convenient real-time input for BCI applications. As you can see, image on the left is our NIRS machine, and on the right is the prototype headband we are using now. We put it on our forehead to get the information from our prefrontal cortex. I want to briefly introduce what is the brain-computer interface. It is a communication system that allows real-time interaction between the brain and external devices. Unlike the keyboard, touchpad, or something else, a BCI system aims to achieve the interaction through their brain activities. Typical BCI systems rely on supervised machine learning models. Usually we require a large-scale labeled data set to produce accurate and stable results. In the past 10 years, NIRS-based BCI applications have been started across very many different scenarios. For example, a piano learning helper. It can detect your mental overload or underload and adjust learning task difficulty levels accordingly. However, we found that for each new applications, we need to build a new task-oriented labeled data set if we follow the very classic BCI design protocol. Let's take our last UIST paper, for example. All the collecting data happened during the pandemic. Due to the safety protocols, we were allowed to invite only one participant every other 2 days, so super painful. And for each user, we need them to sit in the lab wearing the headband, perform the task for several sessions, usually lasting over 1 hour. For our last paper, actually, we collected 27 participants' data, and it costed us over 4 months. It's very, very time-consuming, so not just for the subjects, but also for us, for we operators. So we hold 2 questions here. The first is that, can we reuse the data from a different task, or even from unlabeled data collected when subjects perform their normal activities? The second, for each new application, can we calibrate an existing general BCI model on the new task? Considering this, we want to leverage unlabeled NIRS data to avoid extensive data collection and labeling for each new application. In this paper, we propose an adaptive learning framework. It's called NIRS-X to empower interactive BCI applications. NIRS-X, it has 2 components. First is an algorithm called NIRS-CM. It's an algorithm that pre-trains a general brain activity encoder on unlabeled data. Second is the NIRS-Former. It is a neural network architecture we designed specially for NIRS data. In addition, we released a new data set with 53 subjects. I want to talk a little bit about our data set here. For the data set, we use MBAC task to trigger a different level of short-term memory mental workload from the subject. Some of you sitting here, you may know MBAC is a very well-established task in the experimental psychology. And we believe it closely correlates with many HCI tasks. The resulting data is time series data. One example is showing on the top right. Our model needs to classify which MBAC task the subject is currently performing, given this Windows data. Previously, we collected and open accessed it's a visual MBAC data set with 68 subjects. The new 53 subjects data set changes the task stimuli to audio. Now we are talking about the algorithm we are using. So to build a general brain activity encoder with only the unlabeled FNIRS data, so the NIRS-CM learning algorithm we proposed includes two phases. In phase 1, we use only historical unlabeled subjects data to pre-train FNIRS encoder. Here we design a contrastive learning task along with 6 augmentation methods. You can see all of them, they are here. All these 6 augmentation methods and related to the parameter settings used in phase 1 are based on the suggestions from our FNIRS expert and our own practice. They can preserve clinically meaningful information. The encoder can learn invariants through these data transformations to extract general brain activity representations. In phase 2, we train only one additional linear classifier on users' labeled data. This step is to calibrate the pre-trained encoder with minimum training cost. We also tailored a CNN plus transformer encoder for the FNIRS data, aka nearformer. First, we concatenate spatial and temporal, the convolutional layers to extract their joint embeddings at the very low level. Then we use a transformer encoder to extract global spatial temporal relations. Here are the results from the binary classification of cognitive mental workload. The task we choose is 0 back versus 2 back. For here, 0 back is basically when we are sitting here, we do nothing, that is a 0 back, because when the numbers are popping up, you just press the number, yes, it is. But for the 2 back, so we need to, when we in the task, we need to match the number on the screen and matches with the 2 numbers before. So it requires pretty intensive, the short-term memory. It's not that chill. It's not that too hard because for some memory, the short-term memory tasks, if it's too hard, some participants they may just quit. So we choose the 0 back versus the 2 back. So these are the results from the binary classification on the visual and audio MBAC data sets separately. So as you can see, our methods, the NIRS-X, actually it shows comparable performance to supervised methods in binary classification. Here are the transfer learning results between the visual and audio binary classification. As you can see, the NIRS-X outperforms the supervised baseline by a notable gap. Another interesting thing is that the results shows we are not marrying some of the real internal brain process rather than a more superficial perceptual process. To conclude, we develop a new learning framework, NIRS-X, to utilize unlabeled FNIRS data for building a general brain activity encoder. We showed that the NIRS-X matches or even improves classification performance over supervised baselines. Moreover, with training only one linear classifier for each new user, we significantly reduce the calibration effort. This shows the potential of deploying personalized FNIRS-based BCIs for everyday interactive scenarios. We open access to our data set, our code, and methodology. You can find them in our paper. And we want to thank our friends and colleagues for all the help and the collaborations. Thank you very much. Yeah. Excuse me. With different. Oh, so that's actually a very, very good question. That's something we want to do. So, oh yeah, sorry. So even for the FNIRS, it has very many kinds of FNIRS. Many people here, you may know the EEG, ECG. So we need to, the channels on different places. So what we want to do in the future is for the FNIRS, we not just to test the methodology on the device we use, the data we collected. We also want to test it on other available FNIRS data set. Yeah, make it the real multimodal working. Thank you very much.